I'm going to start chapter 4. Last chapter, chapter 3, we discussed random variables, discrete random variables. Now we have to talk about random variables, but continuous. Okay, so I think continuous case is a little bit easier than the random, discrete case. Okay. Uh, so again, for this, either it is either it is discrete random variable or continuous random variable. It has PDF, CDF. In the discrete case, we call PMF, CDF. And the continuous case, we call the same thing, but in different way, PDF and CDF. Okay, you will see that we have discussed expected values, those things regarding to this continuous random variable. Okay. Continuous random variable, which means continuous mean uh, we have to consider all the values, all the possible values within a particular range, within two values. Okay, within an interval. So uh, here they have mentioned random variable which both of the following are satisfied, which means all the number in single interval. So always we consider a single interval for one particular random variable. Okay, something like from 0 to 100, something like that. Okay, just one interval. But you can divide that one single interval into pieces like sub intervals. Like right, okay, my interval is from 0 to 100 inclusive. Okay, so I can divide that from 0 to 1, then 1 to 10, 10 to 50, something like that. Okay, so all numbers in disjoint union of such intervals. So if I divide my interval like 0 to 1, then 1 to 10, those are disjoint union, right? They are not overlap with each others. Okay, they are separate intervals within my entire interval. Okay, anyway, in continuous random variable case, we should be able to uh, denote, or we should be able to represent all possible values within that particular range. Okay, not a point. Okay. Okay. uh, Check this one, this is really important. Don't forget this point throughout this course. Okay, probability of a probability at a point of a continuous random variable is 0. Okay, probability of capital X equal probability of X equals C. I mean, probability of X equals C, if C is a constant or C is a value, then that probability is 0. Okay, definitely it is 0, because in continuous random variable cases there is no point probabilities, which means probability is 0 always. You cannot measure probability of X equal 5, it is 0. Okay, always. But PMF or discrete random variables, yes, we had that value, but here we are dealing with random variables. Okay, so remember this one last point, probability of X equals C, C is a constant value, equals 0. It exists but 0. Okay, so always we are considering something like less than or equal X less than or equal C, or X less than C, X between two values, something like that. Okay. Okay, with random continuous random variable, same as PMF we talk about in discrete random case, we have probability distributions. That probability distribution we call probability density function, or PDF. Simply we call PDF. Probability density function, probability density curve, doesn't matter. Okay, PDF. Previously we had PMF. Now we have PDF. Okay, you will see the difference in a few slides later. So X says X says the total probability of one is allocate the various possible values of X. So X has many values. Right now, it is not just 1, 2, 3, 4. it is like a range or interval, okay, from 0 to 1. Okay, so now it is PDF. Consider this histogram. We have 10 bits, right? Yeah, I don't know whether you can see it. Start from here. Okay, start from here. You have 10 bars, okay, in this histogram. So once I increase the bits, like here 10 bits, but if I simply split this like 100 bits, so same thing, I increase the number of bits, sorry, not 100, 160 bits, okay, clear? So now you can see in this case, it is hard to see the shape. It is, yeah, you can see in like in between 0 and 2, it has higher values. But once we split it further, like 160 bits, you can see some kind of a shape, right? So once I draw this shape, or once I connect these edges, okay, you will see a curve, something like this. Just draw a curve and remove whatever inside, you will see something like this. So we call this density curve, this because this is a curve. So we consider for the continuous random variables curves. Those curves are smooth curves. Okay, these are smooth curves. Smooth curves. What does mean by smooth? Smooth means there is no lag, or all values you can represent in the on the curve. Okay, it's something like this. This is not a smooth curve. Okay, because there is a lag. Smooth curve means something like this. There is no lags. All values you can represent on this curve. Okay. Okay. So probability density curve, PDF, is same something like this. Not the shape, curve. Okay. Okay. Probability density function. Now you can see this is the definition of a probability density curve, or PDF, probability density function. X definitely a continuous random variable. Okay, so PDF, you can see here we can denote probability of capital X is our random variable, continuous random variable, within two values, which mean within an interval A and B. Okay, equals to integrals. Why integrals? If you need to find the area under this curve, okay, what do you use? What do you use? Integrals, right? To get the sum. Simply to get the sum, you use integrals. Same here. To get the sum under a curve, we use this one, because in a continuous random variable, probability is the area under a particular curve. Okay, area. So to measure the area, we use integrals. That's why our PDF equals to this integral. So you can see your lower bound is simple A, upper bound is B. So your function integrate with respect to X, that variable. Okay, clear? So always probability of X either less than some value, greater than some value, or in between, like A and B. Okay. Okay. Probability, we also call this probability distribution of X, because X is our random variable, continuous random variable. So this is the probability distribution of X. Okay. So if it is a probability density function, or simply I call PDF, if your case is a PDF, or your function is a PDF, it should satisfy two things. First one is that function greater than or equal 0. Okay, greater than or equal 0 for all x. Okay, so your function fx greater than or equal 0 for all x, and also integral, which means the sum. I mean area under that curve from it is beginning to end should be equal to 1. Okay, which means total probability equal to 1. Okay, for an example, consider this. Let me erase this one. Okay, consider this is an example. Okay, consider this curve. So here I'm going to mention here it is negative infinity. This is positive infinity. Okay, here somewhere it is 0. Okay, so area under this curve you can measure by using this, right? From negative infinity to positive infinity, get the sum, right, of that function. So this should equals to 1. Okay, because this is the area. I would say area equals to the probability, something like that. Okay, equals 1. So in any case, the question mentioned that check whether this function is a legitimate PDF or this is a valid PDF. You have to check these two. Okay, if your function satisfies these two, then it's a PDF. Okay. Okay. Simple case. Simple. I mean, the easiest easiest continuous random distribution or random variable distribution is the uniform distribution. This is uniform distribution you can define within any interval. Here it is 0 and 1, but you can define it like simple A and simple B. Okay. General way how we define a uniform distribution: simple A comma simple B. So A and B are values. Okay, that can be an integer value or a continuous value, 4.5, 5.6, whatever. Okay, but within a range. So uniform case. See here it is uniform distribution 0, 1. Okay. So sometimes we denote this like capital U 0, 1. Okay, clear? So it starts from 0. See, in 1, this is the distribution. So once you need to get the area, or once you need to check the this PDF is legitimate or not, you can get the area, right? Which means area is what? This one. 1 times 1, it is 1. Okay, so area is 1. This is a legitimate PDF. Clear? Something like that. So uniform distribution, that's the easiest case. So that uniform distribution we can denote like this. So as I mentioned, a uniform distribution exists within an interval. So in that interval, A comma B, A and B are values. So see, PDF you can denote by simple P or simple F. That's fine. Okay. So these are this is the variable, and these are the lower interval or lower bound and upper bound, or you can call it lowest value and the highest value. Okay. So that uniform distribution exists, or simply we call that X value exists within this range, right? Within A and B. So A and B, within A and B, you can calculate the PDF. This is the PDF of a uniform distribution. 1 over B minus A, which means 1 over upper bound minus lower bound. Always. Okay. For an example, if you have, let's say, example, you have a uniform distribution 0 and 1. Okay, you can calculate fx01, your PDF, like 1 over upper bound minus lower bound, which means 1 minus 0, right? You have to mention what is the range of x. So x within where? 1 and 0. What happen otherwise? I mean, let's say x is -1, possible or not? Or x is 2? No, it is not. Belongs to my PDF, right? So all values, whatever outside this, otherwise means any other x values except whatever within this range is 0. Here it is just 1. Okay, 1 over 1 minus 0 is 1. Clear? Okay. So if you need to show the PDF, you have to write it like this. This is a nicer way to write it. Okay. Otherwise, what happened? You have to show it. I mean, you have to mention it. Okay. So for an example, let's take this one. This is again uniform distribution, reaction temperature in Celsius. So A and B given. So my uniform distribution, -5 to 5, right? Okay. First one is the lower bound, second one is the upper bound. Okay. Clear? Then how do we mention that? Let's say, okay, x. My variable is x. So lower bound is -5, upper bound is 5. So this is, I'm going to write the PDF, square bracket. Then I'm going to write what happened in this range, less than or equal 5, greater than or equal 5, or otherwise. Otherwise, definitely 0, because this function defined on this interval only. Okay, any other x value, it goes to 0. So 1 over lower bound, upper bound minus lower bound, which means 5 minus -5. Clear? Which means this is 1 over 5 plus 5, 10. 1 over 10. Okay, this is the PDF. Okay, they have mentioned question. Okay, so compute x less than 0. Something in between. Yes. Okay. In this continuous case, okay, before I go to this question, you can write this like without equal sign. Simply this x less than 5, less than 5, greater than -5, something like this. This is also fine because we are considering continuous values. Okay, so 5.001 and 5.0000001 doesn't matter. Okay, something like that. Okay, so you can include 5 or exclude 5. That's same thing. It doesn't change your probability value. Okay, so in any case, you can simply write probability of x, let's say less than 5, or this is exactly same as x less than or equal 5. Doesn't change because why? Probability of x equals 5. What's the value for this? 0. Okay, so equal doesn't matter here. Okay. Okay, so you have to compute x less than 0 and some kind of range. Okay, let's do this. As I mentioned, your PDF is this. Okay, 1 over 10 within this range. Otherwise, it is 0. So first one, probability of x less than 0. You have to integrate. What's the lower value? -5. Up to where? It starts from here, -5. So up to this one. Start from -5 to here. So 0 somewhere here. So you need to get the probability or the area in between this -5 and 0. So you have to integrate it from -5 to 0, your fx dx. Okay, simply here fx means your function 1 over 10. So see, 1 over 10 dx, x is the variable. So you know how to get the derivative, right? So constant, you have when you if you have to get the sorry, not the derivative, sorry, how do you integrate this? Okay, sorry. If you have to integrate a constant, it is just constant time x or that variable. Okay, so 1 over 10 times x. So x from -5 to 0. So plug these two and get the value. It is 0.5. Okay, integrate it. And if you have to get the sum, or this can be strictly less than or equal whatever, doesn't matter. Okay. So once you need to get this, what you should do, integrate within that range, right? Negative 2.5 to 2.5, your function fx dx. So your function is 1 over 10. Plug 1 over 10 here instead of fx. So they need to get it. Okay. So I think this is much more easier than the PMF. Okay. You have to just integrate. There's another way to find this kind of probabilities. I'll show you later. Okay. Like using CDF is much more easier than this. Okay. Clear? Okay. That is just for chapter 4.1. Any questions from chapter 4.1? Because I'm going to move chapter 4.2. I mean, need to continue that one. Okay, let me. Okay. Okay. We learned how to write a PDF of a random continuous random variable. If anytime I call it or you have it's in your paper like PDF, which means definitely continuous random variable. Okay. So don't confuse with that. If it is a PDF, then definitely it is a continuous random variable. Okay. Okay. Same as previous cases, we have cumulative distribution function, which means CDF, and also expected values, various. We can calculate those stuff as well. Okay. Okay. CDF. Again, CDF, which means we always measure the cumulative probability from its beginning to at some point. So same idea here. You have to measure its probability from its beginning to, I don't know where it starts from, beginning to at that point. That point is x here. Simple x. This is the value. Okay. CDF, again we denote by capital F. This is the variable and this is the CDF. Okay. So in this case, you don't need to add each and every terms because you cannot do that. Instead of that, you get the integer. Okay, you integrate it from its beginning. This is where it start. Your starting x value. Starting x value. Here, at what point you stop? I mean, from start to what point you measure your CDF. Okay. Integrate from those two values fy. Here they have mentioned fy instead of x. Okay, because you will confuse with this x and this x if you have something like that. So that's why they have mentioned y. They have used simple y instead of x. Okay, but thing is from integrate negative x to negative infinity to x fx dx. Okay. This x is something else and this one is something else. Okay, so don't confuse with these two values. This is this value, this is a value, let's say something like this. Okay, yeah. Each x fx is the area under density curve. Okay, area under the density curve. Okay, I'll draw it. I think we don't have a page, right? Yeah. If I need to measure area from negative infinity to, let's say, simple c. So I need to get the area under this curve from its beginning to this point. Okay, which means negative infinity to c fx dx is my, if my function is fx. Okay, this is the CDF. What we are talking about here. Okay. Again, what is the total probability? I mean, from negative infinity to positive infinity, it is 1, right? This one. Okay. Uniform distribution, this is a recall from the last section. If you have a uniform distribution, you can write the PDF like this, right? Otherwise 0. Okay, remember this one. And if you need to find the CDF, simply what you have to do, from negative infinity to x, this function. Now what is this function? 1 over b minus a. So plug this function here and integrate it. Then plug the upper bound and lower bound. Then you can simply calculate your CDF of uniform distribution A and B. So this is the CDF of uniform distribution. Here I think, yeah, A comma B. Okay. Sometime I don't think they have mentioned here, but sometime if A and B exclusive, then you can again write it something like this: A comma B, but A and B are exclusive. So just simple brackets. Okay. Clear? Because A and B are included, that's why we use this square bracket. You know that symbols, right? Square bracket and normal bracket. Okay, so just to take it. Okay, clear? Everything in this continuous random variable, we deal with integrals or summations. Okay. Okay, more completely. Otherwise, we mentioned here. See this one. For the CDF, you can write it like divide into 2 pieces, something like this. See, in that particular range, you have your CDF, what you calculated in last slide. Okay, the range in between A and B. What happened? Your X value less than A. Now we are talking about CDF, not PDF. In the PDF, you can simply say otherwise 0. Okay, but do you remember the CDF? It is cumulative, right? It is adding something. So always less than this value, it is 0. Greater than that value, it is 1. Okay. Previous cases we had like this step function. Do you remember that? Up to 1, right? This is CDF of a discrete random variable. Clear? Do you remember this one? Something like this. Now we don't have this. Instead of that, we have something like this. It goes up to 1. So after 1, it's remain 1. Okay? Because now we have smooth curves. We have all values. Okay? That's why before your A, let's say here A, here B. So before A, it is 0. After B, it's remain 1. See? In between, you can calculate the value using what you have taken here. Okay? Okay. So this is some kind of like, you will feel that it is so much theories, but once you try to solve the problems, you will see you need these theories. Okay. Okay. X is again continuous random variable. Any number A is a constant value. Constant mean whatever a value. Okay. So probability of X, that random variable, greater than A, you can simply find 1 minus CDF of that value up to that value, which means this is the CDF of this function up to A. Okay, which means this ask probability something like this. Here A, okay, this asks probability this part, this area. This asks the area under this curve from A to its maximum point. Let's say infinity. Okay, so this is what they ask. This is infinity. So this is what this means. Okay, you can simply find area from its beginning to from its start to this point, okay, which is this one, FA, right? So 1 minus FA, which means what you need, right? So you will need this idea. I mean, once we start the normal distribution, you will need this idea, exactly same idea, okay? Because these are continuous random variables, okay? Okay, any two numbers, if you need to find something like this, or simply A less than X less than B, something like this, same thing, okay? Here also, it can be this, because we are dealing with continuous random variable, it doesn't matter, okay? So this is what I told you. I'll show you after a few slides. If you need to get the probability within a range, you can simply use your CDF knowledge, which means FB minus FA. If you remember, in the discrete case, you use same thing but in different ways, right? You did use it like this. If you remember, it is like in -1. You remember that? Okay. But here we are dealing with continuous. Doesn't matter. You can simply use these boundary values what they have given. Okay, it is easy. This is CDF. Okay, CDF values. Simply, this means something like this. Here you have your A. Sorry, this is your A. Here your B. So we need to find this area. So get the area here from its beginning to A, from its beginning to B, and subtract them. Okay. Okay. Check
Hello,
this
sir.
example. This example, they have given a PDF, but that PDF is incompleted. Okay. You need to find something in this PDF. You can see, doesn't matter what is X, what is K. K is a value, or K is a constant that you need to find. Okay, K is a value you need to find. K is a constant. Okay, I'm telling you, okay, this is a PDF. I'm telling you this is a PDF. So you know what's the mean by PDF, right? If PDF is legitimate, or if it is a PDF, it satisfies two things, right? Fx greater than or equals 0 for all x. What's the other one? From its beginning to its end, summation is equals to 1, right? Clear? Okay. This PDF, what is the range of x? X greater than 1, we have our PDF. What happen otherwise? X less than 1 or less than or equal 1, it is 0, right? So you can find this K using that second condition, right? So this starts from where? 1, right? Up to where? They haven't mentioned. So x greater than 1. So from 1 to infinity, right? There is no limit, infinity. Your PDF, K over x to the power 4, okay, right? Dx. Here your variable is x. What is this equals to? It should equals to 1, right? Because if this PDF is a legitimate, or if this is a PDF, then this should satisfy condition number 2. 2, right? Yeah, 2. Clear? So solve this, you can find the K. Okay, this is very common problem using integrals. You can solve this. Okay, clear? I'll show you how we do this, but idea is this. Clear? We use those conditions to solve simple stuff. Okay, determine K. Okay, see, first one we need to find K. If this is a legitimate PDF, we can find K. Cumulative, okay, we need to find the CDF, then we have to find these two values. Okay, let's do that. If it is a legitimate PDF, then is satisfy this one definitely, okay, and this one. So we can use this one, condition number 2, to find this. See, it goes from 1 to infinity. Your PDF. This is your PDF. This is your PDF from here. See, this one. Okay, dx. So you can simply integrate it. Integrate that one. So integrate 1 over x. What is that? Negative 1 over x squared. Right. So here you have to integrate. Forget about k. You can take out k out from this integral side. So 1 to infinity x to the power negative 4 dx. Right. Clear? Or 1 over x to the power 4. So what is this? K times negative 1 over x to the power 3. So 1 to infinity, right? Clear? Integrals, okay? Because n plus 1 divided by n plus 1. Okay? Here n plus 1, n is negative. So n plus 1 means 3. That's why this becomes like this. Sorry, I forgot it. 3 is here. Okay? 1 over n plus 1 is 3. Do you remember that, right? Do I need to remind you how to do the integrals? No, right? Okay. Okay. X to the power negative 1, x negative 4 dx, which means negative, sorry, I'll write it like negative, how do I write it? X to the power negative 4 plus 1 divided by negative 4 plus 1, right? This is how we get the integral. So this is going to be negative 3, negative 4 plus 3. Oh, sorry, this is not negative. So 3, this is going to be x to the power 3, negative 3, which means x to the power 3, 1 over x to the power 3. So, right? Just try to remind you how to get the integrals, okay? So then you can simply plug your boundary values, then you can do cross multiplication, and this is going to be like k times 1 over 3 equals 1. So k equals 3. Okay, clear? So k equals 3. Now you can write your PDF. So you can write your PDF like this. You can replace this. Don't replace here. You can replace this. K equals 3. Okay. Now it's completed. You have complete PDF. Need to find fx. This one. Sorry. What's the probability? Okay. Second one is to find the CDF. Okay. Find the CDF. So you have your PDF. I think 3 over x4. Okay. 3 over x to the power 4 within that range. So see, fx start from 1 up to x, any x value. Integrate this, your PDF. So integrate it, you can get this x greater than 1. This, what happened to x less than 1? It is 0. Okay, clear? It is 1. Up to 1 it is 0, then it is start to increases, then at some point it goes to 1. I mean at infinity. Okay. Okay, so definitely if you need to write the CDF, you have to mention it like this. Okay, you know that because we use the same thing in the last chapter as well. Okay, within a range, it is easy, 2 and 3. So f3 minus f2, right? You can get the value. But if you need to find this again, you have to do some calculations. But it is easy. Already you have found your CDF, right? So what is the CDF? 1 minus 1 over 1 minus 1 over x to the power 3. 1 minus 1 over x to the power 3. So this is your CDF, x greater than or equal 1, right? So simply you have to plug these values, F3, which means x equals 3. X equals 3. Plug that and calculate. Okay. Same here. And get the subtract them. You can find the value. Okay. X greater than 1.5. Simply use the negation 1 minus F 1.5. You can find 1.5 easily. 1 minus that value is what you need. Okay. This is easy, right? That's why I told you this continuous case is much more easier than the discrete case. Okay. Okay. What is this? Okay. If you have a CDF, okay, if you have a cumulative density function, how do we find PDF? Easy. How did you find the CDF from the PDF? You simply integrate it, right? Clear? So from PDF to CDF, what you used, you integrate it, right? Get the sum. So if you need to go back from CDF to PDF, what you have to do? Get the derivative. Integrate, derivative. Integrate it, get the derivative. Okay, like this. Okay. So that's what they have mentioned. We did, you know how to denote the derivative using dash, right? F dash x mean first derivative. Okay. So capital F dash x, which means d over dx, your fx equals to PDF. Okay. Don't mix this capital F and simple x. Okay. Capital X means CDF. Simple F means PDF. Okay. Okay. This piece, this is the last part I'm going to discuss today. This is important. Okay. If we need to find a value which is which gives our distribution to some kind of percentage, like what is the value? What is called? What's the value of 95th percentile of our distribution? Okay, which means, okay, this one. Let me draw this one so it is easy. If you have your distribution something like this, okay, up to this point, I don't know what is the value. Let's say C, up to this point, okay, it has covered 95%, not the probability or whatever, 95% from our distribution. Okay, we need to find what is the corresponding value, which means value here, that x value. Okay, so here x equals C. You need to find this C. That is something what we are going to do here. So they have given the corresponding percentile or that probability value, this 95% mean 0.95, right? So they have given that we need to find that particular x value. So you can find that x value using this. This is what they have given. This is the percentile. So percentile normally gives like 100 times p. Okay, see 100 times p. So your p is a decimal value in between 0 and 1. Multiply by 100, it's a percentage, right? 95%, 85%. So you need to get just that probability value, not the percentage. This is the probability value. Probability value, okay? Not the percentage. So for an example, if I consider 95%, which means you have to get the 0.95 here, not the 95, okay? So P, probability, and you can find your corresponding x value, capital F, that x value. This gives you, this means that corresponding x value. Eta P mean that particular x value, C. How do you find that? You have to integrate your PDF from its beginning to that point. Simply, that's the definition, right? Negative infinity to C, fx dx. This equals to what? This equals to simple P, what they have given. Clear? Similar idea, but using different ways. Okay. Clear? Check this one. See, 95 percentile. So you know your P is 0.95, right? So 0.95 equals integrate. This is start from 0 up to you don't know. So let's say simple C. What is your function? Your PDF. Your fx is this 1 over 8 plus 3 over 8 times x dx. Okay, this is your PDF dx. So solve this, you can find the C. Okay, you can see that values. Okay, in this case here, see, this is P 0.95. This is your PDF 0 to A. It is negative infinity or 0. Oh, sorry, this yeah, this 0. Yeah, start from 0 as I mentioned. 0 to A. Here C mean A. So you can find what is A. Only thing is, if you need to find that particular value, most of the time you will be having a quadratic equation. Okay, see, once you simplify this, doing cross multiplication or whatever, you will be having a quadratic equation. So you know that a quadratic equations, there are two solutions, definitely two solutions that can be overlapped with other, that's fine. But two solutions, you need to pick the correct answer or correct root from those two. Okay, here see two answers for A, but you cannot get this one. Why? Your PDF, that value 0 to what? 2, right? I don't remember that. Yeah, 2. So your range is 0 to 2. So you cannot get value negative 2.6. So only possible answer is 1.94. So this is your C. As I mentioned, your C or A. Eta P. Eta P is just a notation. Okay.